All right, let's start. Good morning. Okay, so today we're going to continue with the chain rule. Okay, so finishing up section 3.4. So first, let's summarize what we learned last time. Last time you learned how to identify an inner function and an outer function, and then use the chain rule to find the derivative. Okay, so we saw that dy dx was dy du, and then du dx, where x was the inner function, the first thing that happens to the composite function, and y was the outer function, the last thing that happened to the composite function. More importantly, we learned that, for example, if you take the derivative of u to the n, where u could be anything that's complicated, a function of x, we knew that this was n times u to the power n minus 1 times du dx. And then, for example, derivative of sine of u was cosine of u du dx. Derivative of e to the u, for example, turns into e to the u du dx. So what we discovered last time was that all the basic rules of derivatives that you know, derivative of sine is cosine, derivative of u is e to the u again, e to the u is e to the u again. All the basic rules you know are the same. And the only thing you need to add to what you already know is the du dx added to the end. All right, so derivative of tangent is secant squared. So derivative of tangent of whatever is secant squared of that thing, derivative of that thing. Everything that you've already encountered is still the same. Now, today we're going to be looking at more complicated examples. The first one we're going to look at is a chain rule within a chain rule kind of situation. Whoa, that's not good. First one we'll look at is y is equal to the fifth root of 3 plus 2 cosine of 4x. Okay, so y is equal to something to the fifth root, and that something could be complicated like what we got here. Remember, the good first step is to just simply rewrite it as 3 plus 2 cosine of 4x to the power of 1 over 5. And now you try to recognize what kind of form of situation you got going on here. If we were to call this thing u, then this is just u to the power of 1 over 5. And that's just the basic power rule application with that du dx multiplied at the end to account for the fact that this thing is not just an x anymore. Okay, so let's take the derivative. Y prime, bring the power down, the basic power rule part. U, all of this stuff we're calling U. Times subtracting 1 from, well, raised to the power of this subtracted by 1. So 1 over 5 minus 1 is negative 4 over 5. Okay, now we account for the fact that this is not just an x anymore. This u here contains a lot of stuff. So we multiply by the derivative of that u, d dx of 3 plus 2 cosine of 4x. Okay, remember this is our u, and this part right here is our du dx. The first part is the basic classical power rule. Bring the power down, reduce the power by 1. Keep the base the same. Now we account for the fact that it's not just an x taking the place, but it's something potentially complicated. Now, if you look at what's going on here, notice that derivative of 3 is easy. But this part here, when we take the derivative, this is another chain rule situation. Right? This is a cosine of something kind of situation. And it's not just a pure x. It's 4x in this case. But in general, it could be anything involving x. So we use chain rule to get to this part. And to finish it up, we need another chain rule within that chain rule. Okay, so let's see. This part doesn't do anything anymore. We'll just keep it the same. Now we take the derivative of 3, that's at 0, of course. Derivative of 2 cosine of blah is negative 2 sine of whatever, right? The thing stays the same. And now we account for the fact that this is not just an x anymore. So we multiply by the derivative of that, which is 4. So this is the derivative of that. And we have that due to chain rule the second time. Okay, does that make sense to everyone? What's going on here? Yes? Good. All right, so what's left here? Not much. Simply clean this up a little bit. Let's do it this way. I have a negative 8. I'll put it on the top. Sine of 4x. And then I'll bring the 5 down here. And I'll put all of this stuff to a positive power downstairs. Okay, so you got chain rule within chain rule. And chain rule happens whenever you have a function that depends not just on x, but something more than just an x. Like here, a 4x. If that 4 weren't here, then that's just a basic first one chain rule and then we're done kind of thing. Here, because we have this thing going on, that's another chain rule application. And so if you have really complicated stuff, sometimes you have to chain this out a few more times. But here, if you get it how to do twice, you can do anything beyond that. Questions? Okay, let's do another one like that. Let's do y is equal to cosine of the cotangent of 2x. And as usual, you work inside out. First go into the most interior part and try to pick something to be your first u, and then go from there. Okay, so why don't we call this thing u here? And so what we got here is simply y is equal to cosine of u. And we know the basic rules of all the derivatives we know are still the same. Now we just got to account for the fact that u could be more than just an x. So knowing y is cosine of u, we know the derivative is minus sine of u times du dx. Here we're going to have to do a little bit more with the du dx when we get there, but as long as you know the big idea here, you should be able to carry out the individual pieces of that. Okay, so here we have negative sine of the same thing, minus sine of u times derivative of what we're calling u. And we're calling cotangent of 2x our u. Here we got the same thing again. We're taking the derivative of some function that depends on something more than just an x. So that's cotangent of something, right? Derivative is, what's the derivative of cotangent? Negative, right? Negative cosecant square of blah times blah prime, right? That's so technical, but you get the idea. Okay, so we got another chain rule within a chain rule. And you can see if this blah here were more complicated, we could potentially be required to even carry out more chain rule. But let's just stick with 2. Once again, if you get 2, 3 and beyond is just the same thing. That part is done. There's no reason to do anything. There's really nothing to do anymore. No reason to touch it. Here we get our negative cosecant squared of that. 2x, sorry. Negative cosecant square of 2x. Multiplied by derivative of that, which is 2. Okay, now not much left here. Let's just clean this up. Minus minus is a plus. There's a 2. Let's put a 2 in the front. And then sine of cotangent of 2x times cosecant squared of 2x. Make sense? Any question on this? Okay, good. Let's do one more along that line. this came from an old exam. So this is from Fall 13, Exam 2. And this exam had a question like this. If h of x is equal to cosine of 2x to the power of 3, then h prime of pi over 6 is equal to okay, so you take the derivative, get h prime of x, and then you worry about that pi over 6. Okay, so one thing at a time. This is in the form of something to the power of 3. We know how to handle stuff in that form. We bring the 3 to the front, keep that something unchanged, reduce the power by 1. And now we account for the fact that something is more than just an x. So we multiply by the derivative of that something. And now you notice that this here requires another chain rule, right? So we get 3 cosine of 2x, the whole thing squared. Here we have cosine of blah. Derivative is minus sine of blah times the derivative of that. And now this is the key part, right? So that was what this question was testing. If you realize that, if the students back then realized that there was a chain rule going on the second time, and one of the 5 choices, of course, included one without that 2. Right? If you didn't realize that there's another chain rule going on, you would not have a 2, then you would have gotten the wrong answer. Okay, now let's plug in pi over 6. So let's see what we get. We get 3 cosine of 2 times pi over 6, that's pi over 3, squared times negative sine of pi over 6 times 2, pi over 3, times a 2. So what do we get? We get minus 6. What's cosine of pi over 3? Cosine of pi over 3 is? That's not good. Cosine of pi over 3 is 1/2. Very good. 1/2. And you bet that if you a different wrong value of cosine of pi over 3 eventually became one of the answers. But anyway, stuff you need to know. How about sine of pi over 3? Yep. Root 3 over 2. So let's clean this up. We get negative 6 over 4 times root 3 over 2. So that's negative 3 root 3 over 4. Without this 2, you would have had an 8 down here, and that happened to be one of the choices. Right? So that 2 there, the chain rule second time, that was the very, very important part of that question. Okay, does that make sense? Chain rule within a chain rule. Everybody gets it? Okay, any question on this example? Be sure you know the values of stuff like cosine of pi over 3 and so on. Otherwise, well, if you got this far and you couldn't find these, and that's kind of a shame. This next one is a situation where we have to use the product rule to start, but then we have to have chain rule buried in after we started with the product rule. So it looks kind of complicated. We have x to the fourth minus 1, the whole thing raised to the power of 5, times x cubed plus 1, the whole thing raised to the power of 8. The first thing you got to realize was that we have a product of two things involving x. So we got to start with a product rule. Anytime you got stuff multiplied together, product rule is the safe way to go. Okay, so we get y prime is equal to, applying the product rule now, we get first times the derivative of the second. So second part here is u to the 8th, right? We bring the 8 down, keep whatever we're calling u for the moment the same, reduce the power by 1, and what else? What do I need here? 3x squared, right? So this derivative of x cubed plus 1. And the reason we have it is because of chain rule. Okay, so that's the first part of the product rule. First thing times the derivative of the second. And the derivative of the second here, we needed a chain rule. 8 comes down. That stays the same. Power goes down by 1 times derivative of that thing. It's more than just an x. Second part, same idea. Second thing we see times derivative of the first. Same form, something to the power of 5. 5 comes down, that thing stays put, power reduced by 1, and now we need a derivative of this, 4x cubed. Okay, so that's also from the chain rule. It's not a chain rule within a chain rule like we did last time. This is just a product rule, but then both parts require chain rule. How do you simplify this? If this were on WebAssign, then you put this in there and it takes it and you're done. Now, but if you're going to do something more to it, you probably want to simplify this a little bit. How do you simplify this? Say it again? Yeah, we could take out the common factors, right? So I see we have a common factor of x to the fourth minus 1. There's a power of 4 here, a power of 5. I can take out the power of 4. X cubed plus 1, power of 7 and 8. I can take out the lower one. I can take out this thing to the power of 7. X cubed and x squared, I can take out an x squared. So that's what I can do. I'll factor out x to the fourth minus 1 to the power of 4. And x cubed plus 1 to the power of 7. You take out the one with the lower power. And then here I have a 20x cubed and 24x squared. So I could also take out, let's see, 20 and 24, they have a common factor of 4, right? 4. 4x squared, thank you. All right, so let's see what we get. We get all of these guys in the front. 4x squared, x to the 4th minus 1 to the 4th, x cubed plus 1 to the 7th. Okay, these guys come out. And now the first term right here is going to lose one factor of that. So it keeps 1. It'll lose all 7 of that, so that's gone. It has 24x squared. I'm taking out 4x squared, so it keeps a 6. Second group, same thing, plus x cubed plus 1 to the 8th. I took 7 of those out, so I keep 1 of that. X to the 4th minus 1 to the 4th, I took all 4 of them out. So that thing is a 1, it's gone. And then back here I have a 20x cubed. I took away 4x squared, so I keep a 5x. Okay, so now we just got to clean up inside those brackets and we are done. So inside here we got 6x to the 4th plus 5x to the 4th. That's 11x to the 4th. Minus 6 plus 5x. There we go. Okay, the big things up here, that's just simplifying stuff, doing algebra. Here we have 2 chain rule applications inside 1 product rule. How would you take the second derivative of that? You do product. Yeah, first of all, you wouldn't, because this is what a pain. But you would do a product rule. You would call these things one thing, these 2 things another thing, and then you got 2 product rule, because you got 1 within each, and then each one of those has 2 chain rule. So this thing just propagates and becomes a huge mess. So you probably don't want to do that. Okay, any question on this example? Yeah. Okay, so first thing I noticed is for example, this guy right here. Both of these terms contain some powers of this stuff. You look at them here, you always take out the one with the lower power. I have one thing to the power of 4, this thing has to the 5. I'll take out the lower one. So I want to extract this from every part of that expression. And then you look for more. We also notice x cubed plus 1. 7 and 8, we take out the 7 one. And then there's a 24 and the 20, so common factor is a 4. And then x squared and x cubed. Take out the lower one, you take out the x squared. Right? Does that answer your question? Okay. Now, I did this, all 3 of these at the same time. If it's more comfortable doing these one at a time, that's fine. There's nothing wrong with that. If you want to do this one at a time, the important thing to remember is to not mess with any of these. Don't bother multiplying them out, because then you lose the factors that you could bring out. Is this next line clear to you? Sure, sure. So these are the things that we've decided to extract out of the entire expression. So that factor out all of these guys out of each one of these. Okay? So looking at, for example, x to the 4th minus 1. In the first group, that thing started with a factor of 5 of those. I'm bringing 4 of those out. I'm taking 4 of those away from it. So it keeps 1 factor of that. This thing had the x cubed plus 1 to the 7th to start. I'm taking all 7 of that out. So that becomes a 1 in its place. Here, this thing had a 24x squared. I took away 4x squared. So leaves me with a 6. Right? Same thing happens here. If you were to multiply all of these back, you should get this thing. We're just reversing that step to make it. We would have 4 things multiplied together as opposed to a bunch of things here added to some other bunch of stuff. Okay, does that make sense? Everyone else, does that make sense? Okay? Good. Other questions? All right. Okay, let's look at other combinations of these rules all mixed together. E to the x times tangent of 2x. First of all, recognize this as something that uses one of the basic stuff you know. If you were to look at this as e to the u, then you know the derivative of that. It's e to the u times u prime. Right? You know how to deal with e to the something. You know how to deal with e to the x, so therefore you know how to deal with e to the u. Because the rule is the same. It's still e to the same thing, derivative of that same thing. You modify all the basic derivatives you know exactly the same way. Just multiply by the u prime. So first step here, we would get derivative of e to the u is e to the u again. Times the derivative of the power this time. Right? That's e to the u, and that's du dx. What do we need to do to take the derivative of this? Product rule, right. This is a product of two things involving x. It's two functions of x multiplied together. That's another product rule situation. So this needs a product rule. And if you look ahead a little bit, there's another chain rule buried into the product rule. Okay, so what do we get? We get y prime is equal to, now notice that we don't do anything with this part anymore. There's nothing to gain from doing anything more to it. Finish this up and see what happens. Now apply the product rule first and second. We get first times the derivative of the second. So what would the derivative of tangent of 2x be? Secant squared. What else? 2x. Is that it? Y times 2. Chain rule again, that's right. Because the derivative of tangent of 2x is equal to secant square of the same thing times the derivative of that, right? We have a tangent of u, derivative is secant square u prime. That completes the first part of the product rule. First times derivative of the second. Now we get second times the derivative of the first. The first is x, derivative is 1. Okay, that's easy. All right, so let's clean this up. e to the x tangent of 2x. Not much left here. It's just, it's that. X secant squared of 2x plus tangent of 2x. 2, yes. Oh, look at that. Thanks. Okay, so the very, very important part of the final answer here is that 2. If this were to show up on the exam, you bet that the thing without a 2 there would be one of the choices. Again, to test if you realize that there's a chain rule going on the second time. Okay, any question on this example? Okay, let's try something interesting here. Last time we took the derivative of e to the x. Let's add more layers to that. Let's try e to the power of e to the power of e to the x. Let's see what kind of mess we get. Actually, let me give you 2 minutes. Give this a shot. See what you get. All right, that's closing after 2 minutes. So what did you get? Who has an answer? Okay, what'd you get? Okay, so he said he got e to the x times e to the x times e to the x. Okay, who got that? Okay, good. All right, if you didn't get that, let's try to find out what happened here. What happened? Math is beautiful, isn't it? All these interesting patterns just fall out of nowhere. Okay, so if you didn't get that, just remember, work these things inside out. Try to recognize whatever you're handed here as something fundamental that you already know. You know how to deal with e to the something. You know how to deal with cosine of something. You know how to deal with something to a power. Try to recognize whatever is happening here as one of those fundamental forms. So if you look at this stuff in here as u, then all you got here is nothing more than e to the u. Derivative of that is simple. Derivative of e to the u is e to the u, where u is that thing. Now we got to pay for the price, pay for the convenience there by having to differentiate what we're calling u. So derivative is e to the u, u prime. Here we got to take the derivative of whatever we're calling u. Okay, now what's going on here is the same thing. This is another e to the something kind of situation. You know how to deal with the derivative. Derivative is e to that something times the derivative of that something. So there's e to the x times. Derivative of this is the same thing to start, times the derivative of, now what we're calling the u this second time. Okay, now this is easy. That's just e to the x. So there's our e to the. I don't know how many e I said, but you get the idea. E to the x times e to the x. So there you go. I'm sure you already see a pattern here. If we add more layers of that, you know what's going to happen after that. What's that? Yeah, that's a good way to put it. Yeah, it'll become increasingly difficult to write these powers. You know, these exponents are supposed to be smaller each time you do it. Eventually, it'll be so small you can't see it. But you know how to handle it, no matter how complicated the power gets. Okay, so now the important point I want to make if you ever run into a situation where you doubt, you wonder if, do I have to use the chain rule in this situation? First of all, if you wonder about it, you probably have to. Second of all, when in doubt, just use it anyway. It doesn't harm what you were supposed to get out of it. For example, if you look at just the pure sine of x, if I want to call this thing u, there's nothing wrong with that. And we know the derivative of sine to the u. It's going to be cosine of that thing we're calling u times the derivative of that thing we're calling u. Right? So what we got here, this is cosine of u, and that's du dx. So here I force myself to use the chain rule even though I don't have to. I clearly don't have to. And you can see, even when I use the chain rule, this is a 1 here. This doesn't do anything to change what I'm expecting to get. So if you use chain rule, even when you don't have to, is okay. It doesn't change what you're supposed to get. All the fundamental stuff can be looked at as if you're calling x u, and that du dx is simply a 1. If you get into a situation like sine of 2x, then right now here chain rule is required. If you don't use the chain rule when you have to, you will get the wrong answer. Not using chain rule when needed will result in the wrong answer. Okay, so let's put it this way. When in doubt, chain it out. That's horrible, but remember that. Okay, chain rule will never harm you even when you don't have to use it. But if you forget to use it, you will get the wrong answer. That 2 wouldn't be there if you forget to use it. Here we didn't have to, but I use it anyway. So I'm just multiplying what I get by 1, and it doesn't change a thing. All right, so make sure you get the chain rule. Chain rule is going to be part of everything we do from this point on. If you're rusty on chain rule, everything from this point on is going to be very difficult. So make sure you really, really, really get the chain rule. That's it. Have a good weekend. See you Monday.